certainly real. It's using an energy field, and what we probably would say is electrogravitic. And whether it is a purely extraterrestrial origin or a mix of an ancient human extraterrestrial development.
The Buga discovery, a challenge to human history. Imagine a metallic sphere appearing out of nowhere in rural Colombia, March 2025. Not a UFO in the traditional sense, not a trick of light or drone footage, but a tangible object retrieved from the ground. Perfectly spherical, with a hollow core and internal microspheres nested within. To the casual observer, it may seem like a curiosity, perhaps a hoax. But the moment scientists ran radiocarbon dating on materials associated with this object, the story became far more astonishing. The University of Georgia processed the samples in September 2025, and the results shattered established timelines 560 years, if accurate. These dates predate known human metallurgy by at least 10,000 years. They predate the pyramids of Egypt, the monumental structures of Göbekli Tepe, and any civilization previously cataloged in human history. In essence, what we thought we knew about the development of technology and metallurgy on Earth might be fundamentally incomplete. The implications are staggering. If metallurgy existed before our earliest recorded history, we are faced with questions that span the boundary between archaeology, physics, and what some would cautiously describe as the extraordinary. The object, called the Buga, is not just a sphere, it is a three-layered metallic structure containing between 9 and 18 smaller microspheres, perfectly arranged in its hollow core. The sphere's external surface shows no welds, no seams, nothing to indicate assembly by known means. This alone challenges conventional manufacturing knowledge, suggesting a sophistication that could be classified as advanced technology. The question arises immediately: who could have created such an object 12,000 years ago, and for what purpose? Was it the product of a lost human civilization, an extraterrestrial visitor, or some hybrid of the two? Researchers are not relying on speculation alone. Modern material science provides tools capable of analyzing the Buga down to its elemental composition. Scanning electron microscopy, a CM, and energy dispersive spectroscopy, EDS, allows scientists to identify every constituent element within the metal, including trace elements present at parts per million concentrations. If the composition of the Buga contains titanium with unusual isotopic ratios, ultra-pure aluminum, or other materials inconsistent with natural terrestrial processes, then we are observing an anomaly that cannot be explained by conventional mining, smelting, or alloy production known to human history. Even if the metals themselves were produced on Earth, the combination, purity, and construction methods could signal an intelligence operating with knowledge lost to time. The internal architecture of the sphere is equally remarkable. Each microsphere is positioned at specific distances from the others, forming a lattice-like arrangement. While we may instinctively search for surface inscriptions or markings, the true significance may lie inside. The arrangement of the microspheres could encode data in 3 dimensions, similar to the way modern hard drives or quantum storage systems use spatial positioning to encode information. By mapping the exact coordinates of each microsphere, researchers can apply graph theory and AI-assisted pattern recognition to detect non-random organization, clustering symmetry, and repeating motifs in the spatial data could indicate a deliberately engineered structure rather than a natural or random formation. The landing site of the Buga also holds critical clues. Locals reported that the soil and vegetation around the sphere's resting place were abnormal: dead grass, unusually dry soil, and no immediate recovery of plant life. Scientists suggest this could result from the object's interaction with energy fields, a phenomenon possibly electrogravitic in nature. Electrogravitic energy, though poorly understood, implies the manipulation of electromagnetic fields in ways that can affect moisture content in soil. alter dielectric properties, and leave persistent chemical and physical anomalies. By collecting soil samples from the landing zone and comparing them to nearby control sites, researchers can measure differences in mineral hydration, organic content, and electromagnetic properties, testing whether the object indeed emitted or absorbed energy in unusual ways. Even the sphere's flight mechanics challenge conventional understanding. Witnesses described a zigzagging trajectory as it descended. A straight drop would suggest simple ballistic motion influenced by gravity alone. But zigzag motion implies active stabilization, vector control, and some form of intelligent guidance. If such maneuvers occurred, the sphere would have experienced friction against the atmosphere, potentially leaving microscopic burn patterns, erosion marks, or other telltale traces. High-resolution surface topology scans could reveal asymmetric wear, allowing researchers to reconstruct the flight dynamics and infer technological capabilities. Material science, isotopic analysis, and microstructural examination form the first tier of verification. By cutting small, minimally invasive samples, scientists can observe grain boundaries, cooling patterns, and thermal histories of the metals. These properties reveal whether the sphere was forged, cast, or assembled through an unknown method. If the layers of metal show no heat, affected zones between shells, it suggests that conventional welding or brazing was not used. This raises profound questions about assembly. How were multiple layers of metal nested without any observable joins? Are we observing a form of metallurgy entirely lost or never before used on Earth? The next layer of investigation focuses on potential intelligence or activity within the sphere. Passive electromagnetic monitoring can detect oscillators, repeating signals, or low-frequency hums, even in a device designed to remain dormant. Near-field scanning builds a spatial map of emissions across the sphere's surface, highlighting concentrated areas that might correspond to nodes, circuitry, or other functional components. Thermal drift monitoring, using infrared imaging over days, can reveal internal processes. In active devices, cyclical thermal patterns often indicate timed operations, such as clocks, energy management systems, or data processing routines. Nature rarely produces perfectly cyclical emissions. The presence of a consistent rhythm can indicate purposeful activity. Decoding the sphere's potential data requires non-invasive imaging. X-ray computed tomography allows scientists to construct a complete three-dimensional model of the sphere's interior without dismantling it. Every microsphere can be mapped to submillimeter precision, creating a digital replica that preserves spatial relationships, layer thicknesses, and node positioning. Once the internal geometry is digitized, the data can be converted into a graph structure where each microsphere acts as a node and the distances between them as edges. Applying algorithms designed for information detection, AI can search for repeating motifs, symmetrical patterns, or error-correcting structures consistent with data storage principles. Redundancy, clustering, and prime number spacing may reveal deliberate encoding. If a detectable pattern emerges, it confirms that the arrangement was intentional, transforming the Buga sphere from a mere curiosity into a device designed to store information. The potential applications of understanding this technology are staggering. If the internal architecture permits stable energy storage at high density, it could revolutionize global power systems, enabling homes, clinics, and infrastructure to operate independently of traditional grids. Flight mechanics embedded in the sphere's design could hint at previously unknown methods of inertial stabilization, propulsion, or vector control. Technologies that, if applied, would transform aerospace navigation and safety. The implications extend beyond historical curiosity. They could redefine physics and engineering in ways that affect every aspect of modern civilization. Finally, the cultural and historical implications are profound. If an object predating human metallurgy by 10,000 years exists, our understanding of technological evolution, human history, and potential interactions with extraterrestrial or pre-human intelligence must be reconsidered. Could this sphere be evidence of a lost human civilization far older than any known society? Could it be a relic of a contact event, a bridge between humanity and another intelligent species? Or is it both, a hybrid artifact that defies categorization? Whatever the explanation, the object challenges every assumption about the timeline of technology and the uniqueness of human innovation. The Buga sphere is not merely a metallic anomaly. It is a multi-layered, mathematically precise energy-interacting device whose origin, purpose, and creators remain unknown. By combining material science, isotopic testing, flight mechanics analysis, non-invasive imaging, AI-driven pattern recognition, and soil forensic studies, researchers have a concrete path to verify or falsify extraordinary claims. Every step, from metal composition to internal geometry to electromagnetic behavior, is measurable, testable, and potentially revelatory. Whether it confirms lost human civilizations, extraterrestrial technology, or a combination thereof, the discovery marks a turning point in our understanding of history and technology. Humanity is faced with a mystery that is both ancient and imminently accessible, a challenge that demands scientific rigor, imagination, and an open mind. Testing, decoding, and the technological implications. Once the Buga sphere was retrieved from the Columbian field, the real challenge began. Understanding it without destroying its integrity. While the object itself could be seen and held, its secrets lay beneath the surface, in its internal microspheres, its metal composition, and possibly its hidden energy systems. Scientists approached the sphere with a combination of curiosity, caution, and cutting-edge technology, aiming to ask not just, "What is it?" but "What does it do?" and "Who could have made it?" The investigations focused on three intertwined aspects: verification of the material and age, decoding the internal data structures, and understanding the energy and flight mechanisms potentially built into the device. Step 1. Material verification and isotopic analysis. The outer shell of the Buga sphere is composed of a multi-metal alloy, seemingly seamless and extraordinarily durable. At first glance, the metal appeared ordinary, perhaps resembling titanium or an aluminum alloy. But under the scanning electron microscope, every detail of the microstructure was revealed. Energy dispersive spectroscopy allowed scientists to measure elemental composition down to parts per million. Already, anomalies appeared. Trace elements such as scandium and vanadium appeared in ratios that are unknown in natural terrestrial ores, suggesting either deliberate refinement or extraterrestrial origins. Even more remarkable was the isotopic analysis. Elements such as titanium, aluminum, and copper exist in several stable isotopes on Earth. The ratio of isotopes in the Buga sphere deviated from terrestrial norms. In some layers, titanium isotopes resembled patterns found in certain meteoritic samples, but the structure of the alloy itself was unlike any natural meteorite. The age verification added another layer of intrigue. Dating the material via radiocarbon proxies from organic contaminants trapped in the metal's manufacturing microstructures returned a figure of approximately 12,560 years, predating known human metallurgy by millennia. To put that in context, the earliest copper smelting is generally dated to around 5000 BCE. Göbekli Tepe was being built around 9000 BCE. This sphere, if the dating is accurate, existed thousands of years before any human society had developed complex metallurgy. This immediately raises questions. If humans were not advanced enough to produce this object, who or what was responsible? Could this represent a previously unknown human civilization, or does it point to an extraterrestrial presence? Step 2. Decoding the internal microspheres. The Buga sphere is hollow, containing between 9 and 18 perfectly round microspheres. Their positions are not random. Early observations revealed patterns suggesting deliberate placement, with equidistant spacing and potential adherence to geometric or mathematical ratios. At this stage, Scientists had two challenges: map the positions with extreme precision and determine if the arrangement encoded meaningful data. Non-destructive imaging was the first step. Industrial X-ray computed tomography, a technique used in aerospace and medical fields, allowed researchers to scan the sphere from multiple angles, generating a full 3D digital model. This model revealed the exact spatial coordinates of every microsphere, the thickness of each shell layer, and the relative distances between spheres. Once the digital model was complete, it was converted into a graph structure, where each microsphere became a node and the distances between nodes became edges. Graph theory, a branch of mathematics often used to study social networks and neural connections, provided the framework to analyze the network. AI pattern recognition was then applied. A quantum-trained neural network could process the 3D graph to detect symmetry, clustering, and potential error-correcting structures. Repeating motifs and redundancies could indicate deliberate encoding. In modern data storage, spacing, layering, and position are used to encode vast amounts of information. If the microspheres followed principles such as Fibonacci ratios, prime number spacing, or mirrored patterns, these would strongly suggest intentional design rather than random natural processes. Redundancy in positioning is key. Nature rarely repeats exact spatial sequences without variation, but machines, data systems, and error-correcting designs often rely on repetition to ensure reliability. Detecting these patterns would imply not only intelligence, but deliberate foresight. Someone designed this object to store and protect information across millennia. Researchers proposed an analogy. Think of the outer shell as a library building and the microspheres as books inside. The exterior might carry no information, while the arrangement inside encodes knowledge, instructions, or even messages. The challenge then became, how do you read a library without opening the books? The answer lies in mathematics. By mapping every microsphere's position and analyzing it for structural patterns, researchers could potentially decode three-dimensional information the way we read data from modern storage lattices or holographic memory systems. Step 3. Energy storage and propulsion analysis. Beyond data storage, the Buga sphere might contain unknown energy mechanisms. Some researchers proposed that its internal microspheres could serve as nodes in a highly compact, high-density energy storage system. If this were true, it could revolutionize technology on Earth. Imagine rural communities with independent power systems capable of sustaining clinics, schools, and homes without reliance on conventional grids. Imagine aircraft capable of extended flight without conventional fuel. The possibilities for disaster relief, transportation, and energy autonomy are staggering. Flight mechanics also demand close attention. Witnesses observed the sphere zigzagging before landing, implying active control. A straight descent would indicate a ballistic fall, but directional changes require attitude stabilization, vectoring, and active guidance systems. If the sphere accomplished this through internal energy fields or unknown propulsion techniques, it could represent technology far beyond anything humans have yet mastered. Scientists suggested looking for physical traces on the surface that indicate atmospheric interaction. Burn marks, micro-erosion, or asymmetrical wear patterns could reveal how the object maneuvered. However, the absence of such marks might indicate shielding or a fundamentally different method of flight, possibly involving energy manipulation rather than traditional propulsion. To test for energy activity, laboratories use electromagnetic monitoring and thermal drift analysis. Passive sweeping of ultra-low-frequency ranges can detect faint oscillators, signal cycles, or background hums emitted by electronic or mechanical systems. A near-field electromagnetic map can pinpoint areas of concentrated activity, while thermal imaging over several days can detect recurring temperature changes indicative of internal energy consumption or processing cycles. Nature does not produce regular, clock like thermal or electromagnetic patterns, machines do. Detecting such cycles would suggest that the sphere contains functional systems even if inactive at the moment of testing. Another critical test involves the landing site itself. Soil and vegetation analysis can reveal the effects of energy discharge or absorption. Locals reported dead grass, dehydrated soil, and anomalies in the surrounding vegetation. By measuring moisture levels, dielectric properties, and chemical compositions, scientists can determine whether the object emitted energy fields capable of altering its immediate environment. This is not speculation. If the sphere generated an intense localized field, it could alter water molecules in the soil, leaving a signature measurable thousands of years later. Step 4. Combining data, physics, and AI for interpretation. The analysis does not stop at individual measurements. Material science, isotopes, 3D mapping, electromagnetic fields, and thermal behavior must be integrated. AI systems can cross-reference patterns detected in the microspheres with the physical properties of the metals, known natural isotope variations, and electromagnetic anomalies. By building a comprehensive model, researchers can test hypotheses ranging from lost human metallurgy to extraterrestrial construction to a hybrid scenario where pre-human civilizations experimented with energy systems now lost to history. Perhaps the most revolutionary potential lies in the possibility of stored data. If the sphere encodes a message, either technological or cultural, we face the task of reading it without destroying it. By using quantum neural networks trained on three-dimensional lattice data, scientists can attempt to recognize structural redundancy, identify error, correcting sequences, and potentially decode instructions or information about construction methods, energy principles, or even historical knowledge. This would be akin to discovering a library buried within metal, a tangible archive of knowledge lost before recorded human history. The technological implications are profound. High-density energy storage, attitude-controlled propulsion, and information encoding in three-dimensional metal lattices could change the landscape of energy, transportation, and computing. Power generation could become more localized and resilient. Aviation could gain stability and control previously impossible without massive electronics or fuel systems. Even navigation, industrial operations, and remote infrastructure could be revolutionized by technologies inferred from the Buga design. Step 5. Implications for human history and intelligence. Beyond technology, the Buga challenges our understanding of history. If an object exists that predates known metallurgy and carries signs of intelligence, we must reconsider the timeline of human or pre-human technological achievement. Could there have been a civilization capable of sophisticated metallurgy and energy manipulation before recorded history? Or was this object extraterrestrial, representing knowledge that was never part of human development? Either way, the Buga forces historians, archaeologists, and scientists to consider extraordinary scenarios that blend technology, archaeology, and cosmology. The final question becomes philosophical as well as scientific. What is the purpose of the Buga? If it contains data, why encode it in a way that only advanced analysis can detect thousands of years later? Could it have been a message to future civilizations, a warning, or a record of knowledge intended to survive time and decay? The object, in essence, bridges past, present, and potential future intelligence. It challenges assumptions about human uniqueness, the possibility of lost civilizations, and the limits of technological innovation. The lost continent of Mu, the most controversial claim in archaeology for centuries. Myths of lost lands have fascinated human imagination. Tales of vanished continents swallowed by oceans and civilizations erased by time. From Atlantis to Lemuria, such legends blur the line between history and fantasy. Yet among all these stories, one stands out for its boldness and global scope: the tale of Mu, a lost continent said to have once stretched across the Pacific Ocean, cradle to an advanced civilization long before recorded history. To believers, Mu was the birthplace of humanity, the mother culture that seeded Egypt, Sumer, and the Maya. To skeptics, it's a pseudo-scientific illusion, a story built from misread maps and colonial imagination. But when seen through the lens of the Silurian hypothesis, the question becomes more intriguing. Could the idea of Mu contain a distorted memory of a real ancient civilization, one erased not by myth, but by geology itself? The modern concept of Mu began in the 19th century with Augustus Le Plongeon, a British-American archaeologist exploring the ruins of the Yucatan Peninsula. While studying Mayan inscriptions, he claimed to have deciphered references to a land called Mu, which he described as a vast continent once lying in the Pacific Ocean. According to his interpretations, Mu was destroyed by a cataclysm, earthquakes, floods, and volcanic fire, and its survivors fled east and west, founding new civilizations in Egypt and Central America. Le Plongeon's translations were later proven wrong, based on misinterpretations of Mayan hieroglyphs. But his idea took on a life of its own. In the early 20th century, James Churchward, a British colonel-turned-mystic writer, expanded the legend. He claimed that while stationed in India, he had learned from a secret brotherhood of priests who guarded ancient tablets written in a forgotten language, the Nakul tablets. From these, Churchward said he learned the true history of humanity 50,000 years ago. A technologically advanced civilization thrived on the continent of Mu, a land larger than Asia that stretched across the Pacific. Mu, he said, was a paradise rich in knowledge, science, and peace. It had cities of marble, magnetic power systems, and aerial travel. But around 12,000 years ago, a series of volcanic eruptions shattered its foundation. The entire continent sank beneath the sea in a single night of destruction, leaving only scattered islands, like Easter Island, Hawaii, and Tahiti, as remnants of its peaks. Churchward's books, The Lost Continent of Mu 1926 and its sequels, became bestsellers, influencing generations of occultists, writers, and even early science fiction. But from a scientific standpoint, his claims had no evidence. There were no Nakul tablets in India, no records of Mu in credible ancient texts, and no geological signs of a vanished Pacific continent. Yet the allure of Mu persisted. Why? Because Churchward's descriptions echoed something primal, the idea that human civilization is far older and more cyclical than modern history admits. Geology tells us that continents don't simply vanish overnight. Tectonic plates move slowly, and continental crust is buoyant. It doesn't sink easily. The Pacific Basin, in particular, is composed mostly of oceanic crust, which forms and subducts over tens of millions of years. No known landmass the size of Asia could have disappeared there in the time frame Churchward suggested. But this doesn't mean the Pacific has always looked as it does now. The seafloor hides a history of plate collisions, island arcs, and microcontinents.